Okay, guys, I want to talk about transition step really quickly. I got the whiteboard on the side here in case I needed to tell you something special, but I wanted to use that slide here because I got a little bit of explanation about how all of this takes place. So the transition step is after glycolysis. So if you learn your output of glycolysis, which is 2 pyruvate, 2 NADH, and to ATP, the net output. You know part of the input of intermediary step because you know it's going to be the 2 pyruvate that will come in here. You will have to have some more NADA plus, NH plus. The reason for that is glycolysis transition step Krebs cycle. It's all about making those electron carriers, NADH and FADH2. Remember that because the electron transport chain will be harnessing all that potential energy to make ATP in numbers. So in this case here, we now transition from the cytoplasm where glycolysis took place into the mitochondrion. In that process, the pyruvate, we will finally, in respiration, expose some carbon dioxide. How does that work? Well, your pyruvate here will lose one of the carbon here. And remember, although that molecule is 3 carbon, the actual formula of the pyruvate, if I can get it to advance, yes. The actual formula of the pyruvate it's a little bit more complex. It has 1, 2, 3 carbon, but it has oxygens and H pluses and H and hydrogens, right? And so that molecule of pyruvate will get transformed. That's how it works. And it's the same thing. We use several reactions at once as during glycolysis for the oxidation of NAD plus to do everything at once. So in the process of being transported in the mitochondrion, that pyruvate will be interacting with a coenzyme A and an NAD plus in the pyruvate dehydrogenase complex. It's thanks to an enzyme. It's always an enzyme. And that reaction will yield carbon dioxide that is lost. So by losing that third carbon, you release kinetic energy from that bond and you use that energy to attach the coenzyme A to the now called acetyl because it's a pyruvate with 3 carbon, and because you have some extra to attach a proton to your NAD plus. And where do you take that proton from? Well, notice how you expose CO2, so you're losing that COO minus here, and you find protons roaming around, right? And you have an additional proton that's left out. But the key process is to understand that here, among those two reactions, thanks to that enzyme, the energy is coming from the shedding of that CO2, taking that COO out of the pyruvate, leading to only having 2 carbon backbone, allows you to both attach the coenzyme A and attach protons to your NAD plus and give you the electrons. It's amazing. And doing all that gives you the output. So similarly to glycolysis, I would encourage you to only learn the output because you know the input from the previous step. And if you know the output, you know the input, right? Look at that. 2 acetyl-CoA, two carbon molecule with a coenzyme A, 2 CO2. Those 2 carbons, they come from somewhere. And if you think about it, 2 carbon dioxide, 2 acetyl-CoA, you get 2 pyruvate because you have 2 3 carbon molecules. But acetyl-CoA has 2 carbon, and that carbon comes with it from the pyruvate. Finally, the 2 NADH, the electron carriers that you always try to accumulate in those steps up to the electron transport chain when you will harness that energy. Then when you know you make 2 NADH, you know you have need of 2 NAD plus 2 H plus. Importantly, why 2 NADH? Because you have 2 acetyl-CoA, because you come from 2 pyruvate. Remember, 1 molecule of glucose, 2 pyruvate. Those 2 pyruvate, we double everything, so you release 2 carbon dioxide, you make 2 NADH, you attach 2 coenzyme A, you make those 2 acetyl-CoA. And here we go. That's really important for us to realize that the carbon dioxide expulsion releases energy. It's an exergonic reaction to break that carbon dioxide away from the pyruvate. We harness that kinetic energy right away to create some potential energy in NADH by oxidation of NAD+, giving it some electron and a proton, and by putting some potential energy by adding a coenzyme A to that acetyl, making acetyl-CoA And that potential energy will be right away used in the Krebs cycle. And for that, we'll see that in the next video. You guys take care.